Hello and welcome to our discussion on linear programming problems. We have solved linear problems using graphical method and simplex method. Now in all those problems, in all those solutions, we had a physical constraint, if you remember, the fifth constraint, which lays down a limitation that our solution, the values of our variables cannot go into negative zone. If you remember the last step, it is always x1, x2, x3, x4, etc. Whatever you are using, a, b, c, w, x, y, z, whatever you are using, should be greater than or equal to 0. It tells me that I cannot produce anything in negative zone. This is x positive, y positive. So number of tables, number of chairs, or whatever we are making use of it for that matter should be positive. If we come in this area, x is negative and y is positive. X is negative, y is positive. Here x is also negative, y is also negative, and if we come in this quadrant, we get x is positive and y is negative. So if you go in either of these quadrants, in this quadrant, if my solution is coming over here, it means that I need positive number of tables, but I need negative number of chairs. X is negative. I cannot produce negative number of chairs. If I come down to this quadrant, negative number of chairs, negative number of tables. This is not possible. So we always have a physical constraint, thereby limiting us to be into positive area only, positive quadrant only. Because I cannot produce negative number of chairs, because I cannot produce negative number of products from a machine. I can produce at most 0, at least 0, anything above that. So this is the effect of x1, x2, x3 greater than 0. At times we call it non-negativity constraint, at times we may call it physical constraint, because it is not physically possible to produce a negative thing. So we can also call it a physical constraint or a non-negativity constraint. Now if at all it so happens in our problem that one of the variables is not constrained, is not restricted. For example, you get a problem where you have x1 and x2 greater than 0 and x3 is said to be unrestricted. In such case, x1, x2 will be positive, but your third variable, third outcome, third product, third output can go into negative zone also because it is unrestricted. Now this is a problem because my simplex algorithm, my graphical approach that I have studied, all the principles that I have laid down, all those are resting on this premise that my x1, x2, x3 will be greater than 0. When I take Cj minus Zj, I am going under this assumption that everything will be positive and then I will try to maximize my returns. I will take maximum Cj minus Zj. So complete algorithm falls down if some variable is unrestricted. So what we'll do is, today we'll take up a question where we'll try to restrict this variable also. Because the complete simplex procedure is resting on this premise that x1, x2, x3 is greater than 0. Linear problem formulation has this step as an essential step. And if this step is not followed, it means it is not a linear problem or it cannot be solved using techniques to solve linear problems. That is the reason we'll take up this kind of problem today and we'll try to restrict x3 also, because otherwise we cannot make use of simplex procedure. So we'll see how we can restrict it. First we'll put down a simple question over here and then we'll try to restrict it. So I'll put up the problem. We'll take a very small simple problem. The problem goes like this: Zmax is equal to 10x1, Zmax is equal to 10x plus 20y, subject to two very simple constraints. What are the constraints? These are 3x plus 2y less than equal to 15. 3x plus 2y less than equal to 15. The other constraint being 2x plus 7y. 2x plus 7y less than equal to 35. And of course, x will be greater than or equal to 0, y is unrestricted. Now what do we do? Where do we go from here? This is not a linear problem, because in a linear problem we have a condition of physical constraints, a non-negativity condition, which states that x and y should be greater than 0, but in our case it is given so that x is greater than 0 but y is unrestricted. Now understand, y is unrestricted. So y can go into positive zone, it can go into negative zone, and it can be 0 also, because y is unrestricted. But I need to restrict y. I cannot restrict y because it is given as unrestricted. What I'll try and do is, I'll put up some value of y. Let that value be p minus q. I'll represent y by p minus q. Now what happens in this case is, if p is equal to q, implies y is equal to 0. If p is equal to q, y is equal to 0. So y can take a value of 0. If p is greater than q, implies p is greater than q. So this term will be positive. Y is greater than 0. And in our third case, if p is less than q, this will imply that y is less than 0. P is less than q. So q is larger. If q is larger, then this solution becomes negative. Solution becoming negative means y is negative. Y being negative is y is smaller than 0. So what I have done is, I have equated y to some two new variables, some relation of p and q. What is that relation? That relation is p minus q. Y is equal to p minus q. But now what I have done is, I have restricted p and q to be greater than 0. So p and q will in either case be greater than 0. Here we can see both of p and q are positive. They'll be equal, we'll be getting a 0. Both are positive. Let us say this was 8 minus 8 giving me a 0. This time p is greater than q. So 8 minus 6 giving me 2. This time p is smaller. So 6 minus 8 giving me minus 2. So y can take a 0, y can take a positive, y can take a negative. But in each case, my p and q are positive, or in other words, greater than 0. So what I have done is, I cannot restrict y because it is unrestricted, but I have restricted the two new variables of which y is assumed to be made of. I have restricted those variables. They will always be positive. This 8 is also positive, this 8 is also positive. Positive 8 minus positive 8 giving me a 0. Positive 8 minus positive 6 giving me a 2. Positive 6 minus positive 8. This is not minus 8. Remember, this is not minus 8. This is positive 6 minus positive 8. This is a difference of p and q. This is not minus 8. Rather, this is a difference of p and q, where p is plus 6, q is plus 8. So now I have restricted the two variables of which y is composed to this condition of p and q being greater than 0. Now if you are making this substitution of y is equal to p minus q, then this formulation changes. What I am saying is, y will be replaced by p minus q. So this complete formulation changes, and this reduces to z max is equal to 10x, x is not changed, y becomes 20. Instead of y, I will be putting a p minus q. Subject to 3x plus 2 p minus q less than equal to 15. 2x plus 7, instead of y it will be a p minus q less than equal to 35. And then last we will have x, there is no mention of y, we will be having a p q greater than equal to 0, because I have restricted p and q to be greater than 0. So my formulation changes to this new one. And then if we solve it for p and q, we will get our final formulation, which would be something like this: z max is equal to 10x plus 20p minus 20q, subject to 3x plus 2p minus 2q less than equal to 15. Then we have 2x plus 7p minus 7q less than equal to 55. And finally, non-negativity constraint saying that x, p and q should be greater than 0. So from an unrestricted variable, now I have reduced my problem to all variables being restricted, and this can easily be solved using Simplex. So we'll go ahead and solve it using Simplex. And yes, we need not worry about p and q. They'll take up whatever values they feel like by themselves, as the case may be. If y is supposed to be 0, then they both will take a value of 8 and 8 or same value. If y is supposed to be greater than 0, p will take a greater value. P will assume a value greater than q. If y is supposed to be less than 0, p will assume a smaller value than q, so that y becomes negative. So we need not worry what will be the value of p, what will be the value of q. We'll just go ahead and solve this as a normal simplex problem. So let us create some kind of partition. Now, how do we get on with this problem? So this was the initial problem, but I made a substitution of y is equal to p minus q so that this condition of y is unrestricted is overcome. And now I have all the variables that I am making use of are greater than 0. And now can we go ahead and find IBFS? If we try to find IBFS for this, my new formulation would be 3x plus 2p minus 2q plus 2p minus 2q. It is less than, so I'll make use of a slack, is equal to 15. Then we have 2x plus 7p minus 7q. Again it is less than, so I'll make use of a slack S2 35. And as a result of inclusion of S1 and S2, my objective function is also updated to be Z max is equal to 10x plus 20p minus 20q plus 0 S1 plus 0 S2. So this is converting the canonical into standard form. Now we can find out our IBFS. IBFS. What will be my IBFS? My IBFS will be x is equal to 0, p is equal to 0, q is equal to 0, thereby giving me S1 is equal to 15 and S2 is equal to 35. This is my IBFS. From this IBFS, I can start my initial simplex table. Fine. How will be our initial simplex table? It will look something like this. Here we'll be having b and theta. Then what are the variables? X, p, q, S1 and S2. S1 and S2, p and q, and there is x. And what are the contributions of x, p, q, etc.? X is contributing 10, 20, minus 20, 0 and 0. What is the IBFS? S1 is equal to 15, S2 is equal to 35. We can close it. This will be our Cj, then there will be a Zj. It is a maximization problem, so we'll be having Cj minus Zj, Cj minus Zj, S1 contributing 0, S2 contributing 0. First constraint is 3, 2, minus 2, 3, 2, minus 2, S1 is 1 and 0. Then it is 2, 7, minus 7, 2, 7, minus 7, 0 and 1. This is our initial simplex table. Let me call it table 1. Now, can we have Zj? Zj is sum product of respective elements. So, 3 multiplied by 0, 2 multiplied by 0, 3 multiplied by 0 plus 2 multiplied by 0 would be a 0. Now, I assume that when we are talking of this particular case where y is unrestricted or any variable for that matter is unrestricted, I assume that we already know how to solve a simplex problem. So, I will just go through the steps assuming that you have seen the earlier videos. So, it will be 0. Now, because of this 0, all of these will be multiplied to 0 at some point of time, all these values will be multiplied. So, 2 multiplied by 0 plus 7 multiplied by 0 is 0, minus 2 multiplied by 0 minus 7 multiplied by 0 would again be a 0, all values will be 0. Next would be Cj minus Zj, 10 minus 0 giving me a 10, 20, minus 20, 0 and 0. This is most positive, thereby giving me my key column. And then divide B by elements of key column. 15 divided by 2 would be a 7.5. 35 divided by 7 would be a 5. 35 divided by 7, 5. So, this gives me my key row. I have my key column, I have key row. This intersection of key row and key column, thereby giving me this is my key row, this is my key column. The intersection is giving me my key element. So, this is our first table. We have our incoming variable is P because it has a potential of improving my output by 20. So, incoming variable is P. Who is going out? S2 is going out because it has least positive decision parameter. So, this is our first table. Now, let us move on to our next table. Next table we can prepare over here. X, P, Q, S1, S2, B and theta. S2 is moving out, so S1 is still sitting over here only. So, we have S1, S2 is moving out and instead P is coming in, P. Their contributions are 10, 20, minus 20, 0 and 0. So, P is contributing me 20, S1 is contributing me 0. Then we have key row. Key row will be divided by key element and we'll get a new key row, modified key row. So, divide everything by 7. We get 2 by 7, 1, minus 1, 0, 1 by 7 and 5. Divide all elements of key row by key element, that is 7. We get this new key row, modified key row. Then for this first row, we'll make use of our formula which says old row minus key column element I multiplied by modified key row is equal to new row. Old row, this is my old row. It says 3, 2, minus 2, 1 and 0. 3, 2, minus 2, 1, 0 and 15. In fact, we have a 15 also. Minus modified key row. Key column element I. Key column, because we are talking of first row, so element 1, first element. Key column, first element, which is 2. 2. Then we have modified key row. Modified key row is coming from here. 2 by 7, 1, 1. This minus 1 will cancel this negative. We have a 0, 1 by 7 and 5. Thereby giving me my new row. New row would be 7 3s are 21, 21 minus 4. making it 17 by 7. 2 minus 2 would be a 0. Minus 2 plus 2 would again be a 0. This is 1. Minus 2 by 7. 12 minus 10. 15 minus 10 would give me a 5. So my new row would be 17 by 7. 0, 0, 1. Minus 2 by 7 and 5. This is my first row. After these alterations, modifications, updations. Why have we done all these modifications, alterations, calculations? So that my identity matrix is kept intact. P is 1, remaining column is 0. S1 is 1, remaining column is 0. This is the effort. Earlier, this was my identity matrix. S1 was 1, everything was 0. S2 was 1, everything else was 0. So my identity matrix should always remain intact. This is why we make these modifications. So once again, my identity matrix is intact. S1 is 1, remaining 0. P and P is 1, remaining everything is 0. So this becomes my second table. Let us call it table 2. This is our table 1. Let us get on with our calculations. We have Cj, here we will be having Zj. All these elements will get multiplied to 0. So when we talk of some product, they will vanish either ways because they will be multiplied to 0. So 17 by 7 multiplied by 0 is 0. If at any time we go for minus 2 by 7 multiplied by 0, it will be 0. So we can leave those. We can get our Zj directly from here. 0 plus 40 by 7. 0 plus 20 minus 20. 0. 20 by 7. Then we can have our Cj minus Zj. Cj minus Zj. It will be a 70 minus 40, making it 30 by 7. 20 minus 20 would be a 0, 0, 0, minus 20 by 7. So this is most positive this time, giving me my key column. And then B divided by key column respectively would give me theta. 5 divided by 17 by 7. 5 divided by 17 by 7. Can I not write it as 5 divided by 17 by 7, making it 35 by 17. And this one would be a 5 divided by 2 by 7. 2 by 7. We flip it, 2 by 7, making it 35 by 2. 35 by 2. So we have 35 in both thetas as numerator, but this 35 is being divided by 17 while this is only being divided by 2. So obviously this will be a smaller value, giving me my key row. So I have my incoming variable as x, outgoing variable is S1. So in next matrix, next table, S1 will be replaced by x. Let us have our table. Now S1 is outgoing variable, incoming variable is x. So I have an x over here, and then P is still intact, not touched P. And then we have their contributions. X is contributing a 10, P is contributing 20. We have Cj, we have Zj, then we'll be having Cj minus Zj. This will be our table 3. So this is my key row, complete key row. Gets divided by key element. Where is my key element? This is my key element. 17 by 7 is key element. So complete key row will be divided by key element. 17 by 7 divided by 17 by 7, 1. This will give me a 0, 0, 7 by 17. Now this is minus 2 by 7 divided by 17 by 7. So 7, 7 cancels out. We get a minus 2 by 17. And then this will be 5 divided by 17 by 7, making it 35 by 17, which you already know. 35 by 17. So this is my key row transport. For the other rows, we'll make use of that formula. What is that formula? That formula says old row minus key column element I multiplied by modified key row. Old row is this one that we need to transfer, 2 by 7. Then there is a 1, minus 1, 0, 1 by 7 and 5. Minus key column element I. Key column element I. We are transferring second row. So second element. Key column second element is 2 by 7. 2 by 7. Multiplied by modified key row. This is my modified key row. 1, 0, 0, 7 by 17, minus 2 by 17. So minus will come over here, 2 by 17, and this becomes 35 by 17. Giving values of, this time we might need this thing. 2 by 7 minus 2 by 7. This would be a 1, this would be a minus 1, this would be 7 and 7 will cancel out, we'll get a minus 2 by 17. In this case, we'll get a 17 plus 4, 21. 21 divided by 119. And then this one would be 119 multiplied by 5. 595 minus 70. 525. 525 upon 119. So this is our new row. We have a 0, 1, minus 1, minus 2 by 17, 21 by 119, and last is 525 by 119. This is our new row. Let me just quickly check it. If it is the same, we have a 1 0 0 0 1 minus 1, then there is a 7 and minus 2 and 21. Perfect. 35 and 75. Perfect. So this is our second table. Now that we are through with these calculations, let us remove this because we are running short of space today. Table 2, and this would be our table 3. Zj, 10 multiplied by 1 plus 20 multiplied by 0, giving me a 10. 0 plus 20. 0 minus 20. 70 minus 40. 70 minus 40 would be a 30 by 17. This would be a minus 20 and 420. 21 multiplied by 20. 420 minus 20. 400 by, sorry, this is 119. So this would be minus 20 minus 140. 420 minus 140. This will be 280 upon 119. 10, 20, 140, 420, 280, perfect. So we have a 280 upon 119. You can go in for your subtraction Cj minus Zj, giving you a 0, 0, 0, minus 30 by 17, minus 280 by 119. This is our table 3. And because all these values are either 0 or negative, so I can say that this is my optimum solution. This is my best possible solution which will maximize Z. Now, what is the solution over here? X is equal to 35 by 17 and P is equal to 525 by 119. Now, the original question was not talking of any P. They were only talking of X and Y. So, what I will do is, I will substitute these values for Y, because the original question only asks me about X and Y. Now, I am giving them answers in X and P, which is inappropriate. So, what I will do is, I will substitute these values to get Y. Y would be, Y is P minus Q. P is this. Y is equal to P minus Q, giving me 525 upon 119 minus Q. Because Q is not featuring in my solution, not featuring in my simplex table, so Q is 0. Whatever is not featuring in this table is always 0. So, I have 0, giving me Y is equal to 525 by 119. So, Z would be 10x, 10 x, Y would be 10x plus 20y. 20y is 525 upon 119, giving me final value of 350 multiplied by 7. So, this becomes 2450 and this one is 525 multiplied by 20. So, total becomes 12,950 upon 119, 108.82, 108.82. This is value of Z, which is maximum possible Z that you can get is 108.82. So, these are my solutions X, Y and Z. Now, if you want, I will put them over here in some different color. X is equal to 35 by 17, Y is equal to 525 by 19. We can simplify it rather. 525 divided by 7, 75 by 17, 75 by 17, giving me a Z of, how much is it? 350 plus 75 into 20, 150, 1500, 1850. Perfect. So, this is my solution of this simplex problem where Y was unrestricted. What I did, I restricted Y. Because I could not restrict Y, I represented Y as a function of some two other variables. Those two other variables were P and Q. Now, because I designed these variables, I restricted P and Q. Now, once Y was being represented by P and Q got restricted, now this became a proper linear problem which can be subjected to simplex treatment. So, from here I started my simplex. This was my simplex formulation. Instead of having X and Y variables, I was having X, P and Q variables. This was my IBFS first table, second table and third table. Third table showing me that all Cj minus Zj's are either 0 or negative. Hence, I can stop at this point, X and P. But now, P was not being asked in main question. So, I went in for substitution. I had X and I had P, but Y was P minus Q. So, I substituted the value P is equal to this thing and Q, because it is not here, so it is definitely 0. So P minus Q, making it y is equal to how much? I have not put the value. Is equal to 525 by 119. Making y is equal to 525 by 119. Then I find out z. 10x plus 20y. 10x plus 20y. Making it 108.82. Or you can leave the values like this also. So this was a linear problem having unrestricted variables. Decision variable gets unrestricted. So it can take a negative value also. But my simplex algorithm is designed in such a way, my decisions are designed in such a way that I am going with Cj minus Zj, I am going with least positive, I am going with most positive. My algorithm is designed in such a way that I cannot go with unrestricted variable. So I decide to restrict that variable, making use of some other variables. So this was it for our today's discussion. Until we meet next time, do take care. Thanks for watching. Bye-bye.